can switch on your camera. Nice. It works.
Okay.
Thank you.
Sorry for the challenges. Okay, so title is semi-self-explanatory, and the reason for using deconvolution I explain in the blue text below that you can read, since this seems to be partly what we're attempting to do in terms of most of our archaeological dating problems. We know something happened, and the problem is how to reconstruct when it happened now, given that it used to exist as an event, and we have managed to create noise and filters in between, both natural ones from archaeological stratigraphy and processes of formation, and anthropogenic ones created by, e.g., humans, both at the time, since, and scholarship. So a starting question, which I'm sure a number of people in this audience would immediately question, is, can radiocarbon actually date something accurately and precisely? And of course, a lot depends on what you're trying to achieve, but in general terms, the answer has to be yes in the modern world, particularly using the recent IntCal 20 calibration curve, which in several periods is a great deal more rigorous than it was before. And we can just pick two examples here. If we imagine that we could manage to find the remains of where Joan of Arc was killed by the English, and we're able to date material that belonged to the year, and we radiocarbon dated that, we'd expect to get the date that you can see in the top left, and it includes very clearly 1431, and we'd get the right answer. This assumes, of course, that we have appropriate samples, we have good associations in the archaeology, we have a good laboratory, we've got good pre-treatment, etc. But even if you have all of those things working out, if we were in 1615 and we were with Samuel de Champlain and we were able to date exactly where he was in 1615, and we just had radiocarbon dates for that context in isolation, we would end up with that very high resolution picture on the bottom right, which clearly doesn't work. We have about a 50% chance of being wrong and about a 50% chance of being about right. And we can't claim that we can accurately or precisely date, and particularly precisely date the 1615. We could claim it's accurate if we said it was anything between about 1450 and 1650. That would be accurate. It's just totally not precise. However, as has been demonstrated repeatedly in applications and studies in the last couple of decades, if you can manage to bring a number of different constraints to bear, it's often possible to overcome that type of ambiguity in the de Champlain case. So where you're able to list a number of different features which describe probability and then reduce the target event probability you're looking for. And this can be done at the site of what's called in modern terms Warminster, but probably was in fact the Chahagi site that de Champlain wrote that he spent the winter of 1615-1616 at, by using a tree ring wiggle match for materials at the site to rule out part of the earlier probability, and then to look at the short-lived material from the site. You can end up dating the site with the best estimate, which narrowly does include the 1615-1616 date that is expected, and therefore it probably does work. Such sequence constraint approaches have been applied in the Mediterranean, and perhaps most famously in the 2010 landmark study by Bronk Ramsey and colleagues, in which they dated Old, Middle, and New Kingdom Egyptian materials and came up with, at the time, a pretty reasonable match between the radiocarbon and the historical expectations, and in fact were able to suggest that at least one of the historical expectation chronologies was probably not correct, but the earlier or higher one probably was. Calibration data has improved since then, which means we have to revisit that. But this study provides something of a landmark study for demonstrating in the Eastern Mediterranean that sophisticated, carefully done archaeological chronology and radiocarbon can come together to provide historically relevant information. If we relook at that information today, and also reconsider some of the rain lengths that we used then, and use, for example, more recent data from either David Aston, Thomas Schneider, and others, and reconsider the analysis, we end up with a very similar result, but with slight, very small differences, and published a paper a couple of years ago in which, for example, looked at the period around Akhenaten and Tutankhamun, and the data come out very closely matching against both the historical estimates of the possible ranges for these rulers and they describe a very small growing season offset between the Egyptian context and the calibration curve. This had already been suggested by Mike D, 2010 et al., and then in the Bronk-Ramsey paper, and we can now estimate that offset to be somewhat smaller, and particularly using modern AMS dates, but we get a very close and accurate result for the Egyptian chronology. And depending on which particular set of rain lengths you use and a couple of assumptions, we can look at the dates that we would get now for a couple of rulers that are of interest to this conference. Year 1 of Ahmes, for example, we have historical dates. I take the ones from Rita Gautsky's paper as just for examples. You can compare them against the original Bronk-Ramsey model, but rerun with best current offset for the Egyptian growing season versus perhaps the current best reasonable chronology for the period using the longer rain lengths that David Aston suggests, Thomas Snyder's reworking of the late New Kingdom. And we get dates that vary from 1559-ish to 1580, sort of top range for Ahmes versus 1564, 1575 from the historical. Given you can see the ones standard deviation ranges include the historical ones, it's again pretty close. But the most notable feature is the date for the beginning of the New Kingdom maybe goes up a little bit, but ironically, because the chronology of the New Kingdom becomes a little bit longer, dates for some of the later rulers actually go down a little bit because the whole chronology becomes longer. And so Ramses II, for example, ends up probably being around 1290 for his accession, in line with Miller's recent work. It doesn't start creeping up into the 14th century. Now, how can we sort of demonstrate archaeological precision and accuracy from radiocarbon in context in the Mediterranean? Shipwrecks are a good test because they provide these time capsule events in which we have a relatively discrete situation. We have a ship being built, it gets used, and then it sinks. That whole process takes place in the course of no more than usually a few decades in the ancient times. Typical ship service periods are estimated at being 20, 30 type of years, not much more. So we have a fairly small window of opportunity. And if we can't manage to date that precisely, that would suggest a problem. The Ulan Burun ship is a nice, for instance, where there is material available from the wood components of the ship, all of which must predate when the ship was actually built and constructed. That will be after the tree rings grew. And then we have material from the last voyage contents, short-lived material, and that will describe dates that are in the years leading up to the exact one. Basically, the ship went down, probably within a few months of the last voyage. And if we look at that set of material against the calibration curve on the bottom right, all of the black equals the wooden samples. They all describe a terminus post quem from quite a bit before if it's inner rings to just before if it's outer rings. And the red ones show the range of the short-lived dates. And what you see is that the red ones tend to be a little bit later, but the range of the black ones starts to rule out quite a bit of the two possibilities that you get from the red ones, such that the earlier range around 1400 is after equals a combination of both the red and the black. So the black means it's a terminus post quem, so it doesn't count. So we end up with the last voyage being where the second option applies with the red ones, which we can then plot as looking something like this. And we get a relatively narrow range of date for when this last voyage occurred. You can't hope to get a date to the year from this sort of thing, but we can try to date it within a few decades. And we get a date that matches pretty well as being just after the Amarna period, which matches against the scarab of Nefertiti. Again, wouldn't appear on the ship if she were not already dead and out of use. More recent example is the Mazatos ship found off the south coast of Cyprus, recently excavated by Stella Domestica, which I've worked on the last few years. Amazing series of finds, hundreds of amphorae, some wood from the vessel of ship, a number of short-lived cargo contents, particularly this vessel filled with olives, and a whole range of different types of amphorae, which for those who follow amphora, even more lovingly described the late Minoan 1A and 1B cups in terms of typology, rim type, shoulders, and otherwise. Now, if we consider the biography of such a situation, we have quite an intricate set of relationships which we can define in time, ranging from when the trees originally grew and were felled, through seasoning, through the fitting out, to the launch, and then the voyages. And we can expect that there is an exponential distribution of the data from that construction through to the last voyage in terms of the material that will be found on the ship, particularly looking at the short-lived material that is found on the ship. And we can model that to try and come up with the best estimate for when the ship will have actually sunk. So in the case of the Mazatos one, we can look at the wooden remains and do wiggle matches to come up with the best estimate for when the ship was probably built, or at least in use. And we then have a phase of contents, which we know must be after that. We can model those together, and we come up with this quite nice wiggle match of the timbers fitting on the calibration curve on the right side in the purpley color. The orange then shows where the olive pits are. There was some dunnage or material for stacking in the last cargo, which is in the green. And you can see they fit on the calibration curve very specifically and very precisely to give us a biography and a timeline of the ship's construction, first voyage, and undoubtedly last voyage at the very beginning of the 4th century. Not only can we just see that, we can actually quantify that and estimate that and come up with a time, for example, for the last voyage, which has about an 8-year or sub-decadal range at 68.3% probability, a little bit larger at 95%. We can calculate the approximate service period. And especially in this case, we can then question previous assumptions. So the published preliminary date from the ceramics placed it in the 3rd quarter of the 4th century. And it would seem that from the combination of the radiocarbon and the dendrite chronology, the last voyage, and therefore the latest possible date for any of these ceramics, is in fact in the early part of the 4th century. And we're looking at about a 50-year difference between the established date from the amphora typology versus what we have. This isn't the first time. A few other studies have suggested that Aegean amphorae in particular need to be relooked at, but it shows that you can use radiocarbon to come up with a almost historical level result in order to question assumptions that have been made from typological studies, which invariably do not have a close calendar control. Which brings us, after relative clarity of these couple of cases, to the controversy in the date of the Thera or Santorini eruption and its general importance. I think it's perhaps worth highlighting the fact that the eruption, in a sense, is unimportant unless it can actually be dated, because its importance only exists if it can be brought into contact with history. At the present moment, we have discussions of different possible dates and ranges, and the fact that that seems to be okay clearly implies that actually we don't really understand the impact and importance of the eruption, or not, because some argue it doesn't have any great significant historical impact at all. But unless we can resolve the date, it isn't possible to actually discuss its importance in terms of the synchronization, history, or otherwise of the Eastern Mediterranean. What do we know about the date of the Santorini eruption? Well, thanks to the recent developments in calibration resolution, we can relook at the possible dates that have been suggested for volcanic eruptions, particularly a paper by Pearson et al. Earlier this year set out a number of possible volcanic eruptions recognized in ice core records. We can look at the perfect radiocarbon date, i.e. what would INCAL say that date was from the calibration curve, and can consider what radiocarbon age would we get for any of those volcanic eruptions. This is actually quite informative and useful because it shows us that apart from the fact that geochemical evidence now would suggest that 1628 signal probably is Aniakchak, which is a different volcano, but in fact, we could see that if the Thera eruption really did date 1628, as has been previously suggested from evidence in previous calibration curves, etc., it would be distinctly different from the dates we have, so we can rule that out. Similarly, if the eruption really happened around 1524 or 1525, as has been suggested by some others, we'd also get a different date. And if it happened around 1500, we get a completely different date. So we can rule out what's not possible, which are those examples. But in between about 1611 and 1539 BC, we effectively get the same radiocarbon date for all of those calendar ages. So that's all of the little distributions next to the purple question marks on the left-hand side, which for all intensive purposes are the same. And if we look on the right-hand side, you'll see why this is on the calibration curve. The three that we can rule out sit at quite distinct different periods of the calibration curve, all of the values between 1611 and 1539 that we cannot distinguish sit across this plateau in the calibration curve, and that's why they all appear to be more or less identical in terms of the radiocarbon calibration age, if we only had that. So this is a classic case like the Samuel de Champlain one at the beginning, in which it doesn't matter how precisely we date the single thing, we can't get a result because there's an inbuilt ambiguity. We're only going to get a precise result, and therefore an accurate result as well, if we can bring other constraints to rule out part of the range of that plateau. So here I summarize and update a recent paper that I published, which discussed this, which if you haven't read, you can always have a look at. And if you don't want to know, you can don't want to know. So the first basic important piece of information is the calibration curve has radically changed in this period, thanks to work now of a number of different laboratories and hundreds of different radiocarbon dates. Period between 1700 BC and 1500 BC is now by far the best dated period of prehistory. This is an important piece of information, but it also means now that radiocarbon-based calibration for this period has a pretty good chance of being fairly accurate and fairly precise, because we have a vast amount of information that's been put into this. So it's not a case of questioning the calibration curve any longer, more of a case of actually wondering what can we do with it. And here we do have a fundamental problem. Apart from the challenge that we have not been very good at recognizing what equals early, late Minoan 1b, and so on in Crete, which was really interesting earlier paper today, we have the problem that unfortunately Crete is one of the most poorly dated in terms of radiocarbon places on Earth for strong archaeological interest. And that reflects the fact that there's been a negative approach to radiocarbon for the last 50 years in a lot of Aegean prehistory. So there's a lot of ground to be made up, in a sense, to compete with the advanced work being done in Northern and Western Europe, North America, Asia Pacific, etc. So what do we know about the dating of the Thera eruption? It's been argued at various times that there are problems to do with volcanic CO2, that there are strange reservoirs, that there are sea mists, that there are all sorts of problems that are meant to have some way of changing the dates that are not understood by the rest of the scientific community. But what we can say is that we now have data that come relevant to the Thera eruption from either tetrafall or direct tsunami impact, particularly the recent exciting paper by Vasif et al. In Turkey, in which we have radiocarbon dates well away from Thera, which can have nothing to do with any possible volcanic carbon CO2 impact there. So that's dataset A that you see on the screen. We also have material from Thera itself, which is not strictly from acroteria, which is either from olive wood or other material, which also relates to the eruption. And we can compare that. So that's dataset C versus A to see whether there's any difference, because the ones from Thera, are they affected by some volcanic effect? And then we have the dates from acroteria, from the excavations, from the final phase, which have been much discussed in the past. Again, we can compare them then against dataset A and ask, well, is there any evidence of a volcanic offset? And finally, we have quite a lot of other data which were run in the period from the 1960s onwards. People dated the Thera eruption based acroteria and elsewhere, and we can compare those data, even though they're much older and less precise and maybe less high quality, and consider whether they're different. And if you look at all of the plots of the combined dates on the left under A, and if you then compare those probability distributions against each other, so A versus C, A versus B, C versus B, A and C versus B, A versus D, A and C versus D, which is what you see under B, you'll see that there is a very small to, in fact, basically zero difference between all of these distributions. The mean differences vary by a couple of years around zero. So they're very small. So there's zero evidence, both from acroteria itself, comparing that against sites that are well over 100 kilometers away from acroteria and Thera, on Crete, but also in Turkey. There's zero evidence of any apparent offsets, reservoirs, or problems, which would imply that we can use this combined set, which means that we're towards now 300 radiocarbon dates in total from the Aegean region relevant to Thera, to come up with the best date for the eruption. The other really important piece of information is we do have a clear stratigraphic sequence that leads up to the time of the eruption, and this hasn't perhaps been used sufficiently in past work. And good summary was in the recent article by Evans and Floyd McCoy. And I just describe here the 5 different stages of eruptive activity that we have. And the critical thing is, even though there's a teeny bit of debate between Susan Limmery, who argue a period of several years, versus others who've argued for a much shorter, weeks, months, days, to a season, to a few several years, we know that there is a very short period of time between basically stage 3, so that's the sort of beginning of the first signs of renewed seismicity or the eruption, or 4, beginnings of the actual eruption series, and then the 5, the final Minoan destructive eruption. So in the picture on the bottom right, the difference between the brown soil layer and the first Plinian fall that you can see, and the 3 layers above that one, the 4 altogether, that whole sequence takes place in a pretty short time of between weeks, months, to a period of several years. So we can use that as an important constraint. So I considered 2 different ways of looking at this. One is the short constraint, which is to say that it's got to be a period of no more than a few years, which you can see on the right-hand side, which means it's most likely to be around about 2 or less years, but it could be up to about 4 or 5 at 1 standard deviation, and it could be up to about 10 at most at 95.4% probability. And the alternative is the very short, which means it most likely happened in a period of a couple of months. It might have happened at 68.3%, probably a bit over a year, and it might just possibly have made 95.4% probability of about 5 years. So we have to constrain the dates within those assumptions. But by using a log normal distribution like this, if the data doesn't agree, it can overwhelm this prior. It's not a fixed prior like using a uniform assumption. And doing that, we can look at the dates from Akrotiri that relate to the final human presence. So that's the stage 2-3 boundary. And then we can look at the dates from the tsunami, tephra, and other destructions which equal the eruption, so stage 5. And we can see that they're very similar, but the TE5 ones, the stage 5, are ever so slightly later. And we can look at the difference between those results, and we see that they model very well against the assumption of a couple of years difference between them. That's B there. And then we can look at the calibration curve and ask, does this make sense that we're actually looking at something that seems to be compacting all of this evidence into quite tight time interval? And of course, lo and behold, there's this dramatic steep slope in the calibration curve, nicely defined in the recent data, to which all of this information seems to fit very closely. So we have prior information like the terminus post quem from the Miletus oak wiggle match, which sits along the little plateau leading to the period just before 1600. Then we have all of the stage 2-3 and then stage 5 data cascading down this period of just a few years, either side of 1600, which gives us a very specific and particular fit. And it's difficult to see how that data can describe a period either earlier than that or later than that. Since that paper, there's been other materials either become available or could have been used, and other materials clearly going to become available. And there's information, for example, paper on site at Mitru tomorrow, which will provide more and more evidence. So I've revised the studies using at present, depending on which version I use, somewhere more than 275 dates versus the 257 used in the paper a couple of months ago. And I just show here to try and let you see how do these models work. What are you thinking? The structure. I've got 2 models, model 1, model 2. Model 1 describes the stratigraphic and time sequence in these terms, in which we have information that comes from before the eruption, and then information from after the eruption that provides then a terminus antequem backwards. And the one thing we do not know is how long between the actual eruption and the sort of close or late LM1B period, which is where we have radiocarbon data at present available from Crete. The others we have some descriptive function on. In particular, we know that the difference between Akrotiri stages 2-3 at the top and 5 is this very short interval. And we have some other information like the famous olive branch and the Miletus oak that we can feed in and say provides a terminus post quem for that stage 5 point. They must date before the eruption. Model 2 is slightly more complicated. It adds in some extra Aegean evidence, so other sites, so Rhodes, Miletus, and other places. And in the period afterwards, it adds some information in from other sites like Colonna, Icklina, and others to create a slightly more complicated Aegean-wide sequence. And it involves adding in another 20 or so dates. I show some of the examples that come out. So here we have model 1. Model 1 doesn't use all of the rest of the Aegean sequence and sites like Chronos, for example, on Crete, merely focuses on the Akrotiri and other Theran-related and directly associated with the tsunami, Therafall, etc. evidence. And we get probability distribution that looks like this with the latest evidence, which most of the probabilities you can see is situated somewhere around 1600 and particularly just afterwards, so particularly in that range, maybe around 1590s into the 1580s. And if you're taking the 95.4% range, you can see 1609 to 1563. So this is a significant shift from in the past, and certainly positions that used to be possible from radiocarbon, previous calibration curves, which pointed maybe 10, 15 years earlier. So we're now looking at the early 16th century rather than the very end of the 17th century. However, suggestions of dates around 1524 to 1525 appear to be beyond the radiocarbon probability, and suggestions around 1500 BC are sort of distinctly beyond the radiocarbon probability. And even a date that's around 1561, 1560, to try and suggest it might just link with the beginning of the New Kingdom is also struggling, although I'd highlight the fact the radiocarbon evidence would suggest the New Kingdom itself perhaps is wandering a little bit further to the left in this diagram and maybe can still come into play. Different models provide slightly different results. So I just show here a couple of different runs to give you the idea that there's small variation, but the variation is small. And you're looking at changes in this 68.3% range from like 1607 to 1586 to 1605 to 1588 and so on. The biggest change tends to be at the very extreme edge. So you'll note that sometimes the probability for the 99.7% range, which is not usually used in archaeology, creeps down to sort of 1538. Other times it only reaches 1545. The very end is poorly described, whereas the upper end and the left-hand side is well constrained, but the right-hand side is less well constrained. This here shows the very latest and lowest model of about 100 and something runs that I have done. So this is sort of as far as you can push it, as far as the current radiocarbon evidence goes without adding in new evidence, which is yet to become available. And it gives you 1607 to 1586 as the most likely range for the eruption. There's one other possible piece of evidence that could be introduced, which was the paper by Badetscher et al. 2014, in which they argued that a signal in the Sophola Speleothem maybe was consistent with the Thera eruption. It's not a lot of other obvious regional causes for what would be creating the chemical signal they recognize. One can question aspects of the possible dating and other things, and it's only approximately dated, the core plus or minus 20 odd years. But if you do include their evidence within the model, that very clearly and strongly supports this region at the beginning of the 16th century more clearly than before. So where does this leave us in summary, and what's actually interesting about this? Well, as I've said, arguably the date itself isn't interesting unless it has some historical association. And here I would like to suggest that the most important factor would appear to be that we have a significant piece of missing information as to what happens in this early LM1B period and its contemporaries across the Aegean. And in particular, if we look at the radiocarbon evidence we currently have, both from the mainland and from Crete, for when later, and I stress later, LM1B, and when LH2A to 2B begin, we have this period from somewhere around about the sort of 1580s through to about the sort of 1550s, where we really don't have any evidence. And we're missing evidence at this point. And yet this seems to be the very time, based on the mainland evidence, and particularly we have the Lerner shaft grave, where we do have some dates, where we're talking about the rise and high point of late Helladic I Greece. So particularly like the later shaft grave circle A. And I therefore sort of wonder whether we aren't actually missing a key generation of time. And it's the chapter that perhaps should have been in Jack Davis's book, which is what happens in the period between the end of late Minoan 1A on Crete and this interval when Crete if we look at, for example, the work and modeling work of Karl Nappert, we'd be seeing major changes in regional trading routes. We'd be seeing concentrations and efforts of doing different things compared to the past and reaching out. The Minoan colonization or the Minoan influence or the Minoanization period begins obviously before the eruption and is very intense up to the time of the eruption. What happens in that period afterwards and how do local elites work when things change dramatically? It's a moment of both opportunity, change, and a moment for ambitious people to step forward with new ideas and new approaches. This may be a very key formative moment for Mycenaean civilization. So we look at the overall Aegean picture on the left-hand side, dates for various sites and phases, and we see the sequence leading up to the eruption. We then have Lerner Schaafgrave 2, which is late LH1, which could be contemporary with Thera, but actually stretches on. We have the evidence at present from Colonna from the article of 2010 from Wild et al., in which again we see it stretching on into the 16th century. And then we have the late Minoan 1b destruction, so N, destruction dating we have from Hania, Metaspogos, and Moklos. Those two LH1 late and LH2 periods across the middle of the 16th century are both our worst evidence, and yet it's probably the most interesting period in later Aegean prehistory at present, where we need to try and find out a great deal more. The difference in time between the eruption and the Cretan destructions, B in the bottom right, is around a century. So it's very difficult to see how we can relate the eruption in any sense to the Cretan destructions. And it's a very long period of time. So there's a lot happens within what is labeled as LM1B. And probably we almost need to create a new subphase at the beginning to be looking at this formative phase. And I just highlight the Karl Nappert et al. Paper that when we're looking at the Aegean region, we have the Thera eruption, end of late Minoan 1A. Late Atlantic 1A undoubtedly carries on somewhat further. And that transitional period between then early late Atlantic 2A and then early late Minoan 1B appears to be when we have the formation of our new political entities that become Mycenaean Greece. And how does this then relate to this vacuum in power that relates around not necessarily destructions on Crete, but dramatic changes in trading routes and other relationships, which would have followed from the destruction of Akrotiri and Thera, and undoubtedly a major impact in parts of the north coast of Crete. Thank you very much.
That was great. Oh, sorry.
The microphone was not open, so
Oh, right.
it's open now.
Right, the microphone is open now. Thank you very much, Stuart. And nice to see a very positive paper of overcoming ambiguity, as you say. I just wanted to put a couple of points in. I'm not going to deal with, I'm sure Jan will have the odd comment about later things, but just out of interest, the work that Karl Nappert and I have done, and Matthew Zaki on Middle Minoan 3A at Chronos, we're fairly convinced, I think, that this period is much more extensive than previously thought, and very much longer than Middle Minoan 3B. If we give 3B a maximum of 25 years, I would think that's generous. Secondly, I wonder about the context of the Chronos twig, which is said to be early LM1A, but I think now we would put most of Chronos early LM1A into Middle Minoan 3B. Anyway, that's just a couple of comments from me, and then I'll pass the, and I don't know whether you want to comment on that.
Nice to see you as well, Colin. In terms of the LM1A, MM3B, in a sense, for this particular analysis, it doesn't matter because they're being used in each case as a terminus post quem for what comes following. So that really would literally be a case of changing the label. It doesn't change the calculation as to what happens with the Thera eruption boundary. But in the wider terms, this relates also back to some previous discussions on the Mesorathology, that trying to better determine what equals MM3 and 3A to B versus early, so-called early LM1A transition. That is a really important point, and undoubtedly that I think is a longer period. I would agree with you.
Thanks. Now, questions from the floor and from the the ether. Right, Bernard.
Hello. Yeah. Nice to see you again, Sturt.
Say your name.
My name is Benny Wellinger, and I don't know whether I should ask this question, but I think we all know this, that I have been criticizing the use of concepts of probability in radiocarbon imaging dating. The last 40 years I've written criticism every now and then, over and over again, and just recently there's another paper coming out where I try to demonstrate that the radiocarbon calibration is actually a Fourier transform, not to be mistaken with a Fourier sum of sines and cosines. It's a simple quantum mechanical Fourier transform. I don't know whether this is your way of thinking, Sturt, but I think you know the arguments I've put forward. That's a sort of simple question. What do you think of the possibility that the underlying probability concepts of Bayesian radiocarbon dating or calibration altogether are flawed or wrong? The concepts we are using and you are using, we can, for example, add probability as if we have dice, that they could be somehow wrong. That may affect your conclusions. What do you think of these concepts I've been putting forward over and over again for the last decades? Thanks.
Well, first of all, obviously, I always read your papers, Bernie, with great interest, and it's nice to hear you. You have, as always, some really good points to make, and the only thing I would highlight here is, and that was part of the reason I threw in the example with Samuel de Champlain and then the Ulvenbrunn shipwreck. There, a simple ad hoc parametric approach, which is simply you describe, you've got event A, then B, then C, and if you can indicate that event A must overlap with B, and therefore both are before C, you can narrow the probability down. In this situation, we can basically avoid using a Bayesian approach. So that would be my response is, yes, I take your point, and I keep focusing and always interested to see what you have. But in this particular case, and therefore the Thera case, it can be done using a simple classical approach, and therefore doesn't strictly rely on whether you are using, a Monte Carlo approach, Gibbs sampling, or how you particularly are trying to model the probability. Where I fully agree with your point that there are some assumptions which have not been fully demonstrated.
Are there any more questions from the floor? Do we have any questions from online? Well, Sturt, sorry, no more questions.
Yeah.
But thank you very, very much.
That's fine. See you.
Bye.